Hello, class. This will be a recorded lecture for section 6.4, which starts the introduction of logarithmic functions. I've been teaching math for a while now, and two things that I've realized is most students struggle with fractions and struggle with logs. And I think one of the reasons why struggle with logs is, first of all, they're not really used very much, and they're not like common practice with regards to any type of normal discussion. And number two, they do have some specific applications that are really important. And so that's what we're really going to focus on. So I'm going to do a quick introduction of the graph and where logs actually are derived or where they come from. And so the concept here is we need to find an inverse of an exponential function. So we have a nice closed form for solving exponential functions. Many things in the world are modeled with exponential functions that we'll talk about quite a bit later on in this chapter. But how do we solve those? Well, the main reason why we introduced this idea of inverse of functions is to introduce a log function. And the definition of a log function is it's an inverse of an exponential. So if we take a look at how we talked about calculating inverses, if we start with the equation y equals 2 to the x, and I said take the inverse. Well, you remember basically what you do is you flip-flop the variables, right? So if we flip-flop the variables, it would be a y turns into an x, and the x turns into a y. And so those are the inverses. And so with regards to a quick graph, you'll see that now if we do y here and x here, if y equals 0, 2 to the 0 power is 1, right? If y equals 1, x would be 2. If y equals 2, x will be 4. If y equals 3, x will be 8, and so on and so forth. So you remember when we did the blue one? Let me do the blue. Whoops, wrong color. Let's see here. Erase that and turn to blue. Okay, here we go. And we did x and y. And remember, when x equals 0, y equals 1. When x equals 1, y equals 2. When x equals 2, y equals 4. When x equals 3, y equals 8. So you can see how things flip-flop, right? X's change to y's and y's change to x's. And so with regards to what the graph looks like, well, again, when you take a look at plotting these, you would see that it would look like this in the slide here. And so this is what we originally did here, right? These are the positive values starting at x equals 0. I'm sorry, when x equals 0, y equals 1. And when x equals 2, I'm sorry, got it backwards. When x equals 4, y equals 2, and as we continue up that way. And if we went in a negative direction, it would flip-flop just like the exponential function. If you remember when we put a negative value in for x, what would end up happening? We would flip, right? And it would be 1/2, 1/4, 1/8 as x becomes -1, -2, -3. So you see what happens here on the y value, right? As y now goes -1, -2, -3, our x value becomes the fraction. So you can see the log function is always positive. You can see the whole graph is always to the right of the y-axis, which implies the x values are always positive. A very important graph is this one here, where you can see that this is what we mean by inverse. The gray is our original exponential function, and the red is our log function. And you could see that the reflection around the identity of y equals x is indicated there with regards to that dotted line. And so a couple key attributes. All log functions pass with regards to when y equals 0, x equals 1. And so it always crosses the x-axis at 1. Doesn't matter what the base of the log function will be. The other thing that's real important, as you can see by the graph, is the log function is always positive. What does that mean? Well, you're never going to get a negative function or a negative number, excuse me, when you plug a value into a log, right? When you use your calculator. So make sure that you do realize that as well. That's always a good check. If you get a negative number for a log, and you say, oh, I did something wrong. So what we do here in the math world is we have to organize these functions where y equals something, right? And you can see that we had x equals 8 to the y, right? 2 to the y in that example that we gave. And so what mathematicians have done is define this log function as a number y such that x equals 8 to the y. And there are two things that is really important about log functions, and this is one of them. To be able to understand that when you have a log function, you can actually convert it to an exponential function by that relationship. And here it is. And so what we want to do now is take this relationship and start understanding how to deal with it. And you'll see that in your homework in my math lab, there is quite a bit of problems where you're given a log function and it asks you to rewrite it as an exponential. So let's walk through a few of these examples now. See if I can get the whiteboard up. There we go. Okay, so let's just walk through a few examples, but let me write the relationship up here, and you should keep this handy. It'll come in handy pretty much the rest of the semester. So if you look at this A value is called our base. And then the X value is the argument inside the log. And then the Y value ends up being the exponent. As we talk about inverses, right? You can see how those two are inverses of one another. And again, it's really important to realize that the value that you put inside the argument of the log function is always going to be positive. Again, we saw that from the graph, right? Let me pull up the graph again real quick. So if you take a look at the graph, right, you can see that the X value is always positive. So you can't put X equals -1 in for the log, it's undefined. So if you think about domains, and I'm probably sick of that, right? But the domain of this function is from X equals 0 all the way to infinity, but you can see log of 0 is undefined as well. And so one of the things that we can just do here is the domain of the log function is 0 to infinity. Okay, so let's take a look at a couple examples here. So say like we had this example, log of 9 base 9 of 3 equals y. And I said, rewrite that into an exponential function. So let's take a look at this. Well, the base is 9, right? So the base would be 9. the argument comes out here, so that would be 3. And what would y be? Y is our exponent. So that's how you rewrite it. And if you wanted to solve this, right, it would look like this. 3 equals what? 3 squared to the y. So that would be 3 and 2y here, right? So remember, it implies a 1 when there's no 1 there. So when you solve for that, 1 equals 2y. So what does y equal? Y equals 1/2. And as I alluded to in the last lecture, that's a square root, right? So when you take the square root of 9, what do you get? 3. Okay, walk through some more of these. I think the best thing is to show you a few examples, but okay, let's try another one. So say like we try this one. Log, and so base 10 here of 10,000 equals y again, just to make sure we mimic that. So how do you rewrite it? Well, the 10's the base, all right? Y, and then this would be 10,000. The base 10 is on your calculator, so you could just use your calculator and you would see that you could rewrite this as 10 to the 4th power equals 10 to the y. And so what does y equal? Y equals 4. So until you get familiar with logs, I always recommend, it's really nice to convert these and see what happens. So let's do a couple more. Let's do this one. Log of, say, base 6 of the number 1 equals y. So what do we do with that one? Well, let's convert it. So the base is 6, right? So we have 6 to the y here, and the argument is 1. And you look at that and say, what do I do with that? Well, remember, by our definition, anything to the 0 power equals 1. So here's the case where y would end up being 0. So another aspect of a log function, right, is that if the argument, as we define as the x value, is 1, y would end up being 0. And we saw that on the graph because it always crossed the x-axis at 1, 0. So it doesn't matter what the base is, that is always the case. Let's see here. Let's pick one more to kind of walk through. Let's see. Let's do this one. So say like you have log, we'll just do 2 more, equals y. So again, base is 2, exponent is the output, and the argument of log is like that, and you know that is 2 to the 3rd equals 2 to the y, so you could see y equals 3. What if we change the base and it ends up looking like this? Log of base 8 to the 8 equals y. So what would y be? So if you rewrite this again, 8 to the y, right, equals 8. Well, remember, that's a 1 there. So then y equals 1. So another thing to remember is that an argument in the base, if you do it in a log function, it always equals 1. And so I think that's a good place to stop this recording, and we'll finish this section in the next recording.